Hi, welcome to the Signal Path. I have a really interesting episode for you guys. We're going to take a look at these light wave transmitter and receiver modules from HP. These are basically electro-optic and optoelectric converters. You can see that there is a yellow fiber that goes between them. You can modulate the light on this one and then receive it on the other side and get the electrical signal back. Now, I really want to dig deep into this, looking at the architectures of how they're built, even taking them apart and looking at the optical devices that are at the heart of these two instruments. This should be pretty interesting. I also want to completely characterize this link and see what kind of signals we can send over this, what kind of analog and digital signals. That should also be interesting. And I want to do all of that using the Siglent ecosystem and see how far we can go using their equipment. So there's a lot to talk about, from teardowns and experimentation and some cool metrology. So let's get started. So let's take a look at the block diagram of these instruments before we take them apart and start characterizing them. Here I have the block diagram of the transmitter, and at the heart of it is the laser diode, the source of our optical signal that we are interested in. Now, this particular laser diode is a DFB laser, distributed feedback laser, and I think I have covered DFB lasers on the channel before, and we've even measured them. But just to recap, a DFB laser has a distributed Bragg structure along the active region of the laser itself. All lasers need some kind of a structure, some kind of feedback to laser the specific wavelength. Now, the material of this laser diode is indium gallium arsenide phosphide, and that's going to give you a range of wavelengths that this laser can actually emit photons, and that's essentially the band gap energy of those materials. But then the Bragg structure spacing is going to determine the exact wavelength that this laser can operate at. In this case, this is a 1310 nanometer. So this DFB laser is going to turn on once you give it some current, and it's going to laser hopefully at the wavelength that you want. But there's a lot more complications here. There are many things you need to control about this laser diode for it to be stable. First of all, the current that you put through the laser diode does move the wavelength to some extent, so you need a very good biasing circuit. And you can see that we indeed have some kind of a bias level control over here that's going to control exactly the amount of current that's in the laser. But it's a bit more nuanced than that, because you also want to control the amount of optical power coming out. So this DFB laser happens to emit in two directions, one forward and back. The back side, they have connected to what's called a back phase diode. This diode is going to measure how much optical power is coming out of this laser diode, which is going to be proportional to the amount of current that you are putting into it. So electrons translating into photons. And it's going to measure that constantly and adjust this bias in a feedback to put exactly the right amount of current to get the optical power you're looking for. That itself is going to stabilize the wavelength to some extent. But as with most optical things, you need temperature control. Temperature moves almost everything in optics and optoelectric devices. So there is a thermoelectric cooler in here, and that thermoelectric cooler is connected to a temperature sensor. So the temperature of this DFB laser diode is constantly being monitored, and this thermal control is in a feedback trying to stabilize the temperature. So by the combination of level control and thermoelectric control, you can then stabilize these lasers DC output powered, optical output power, and its precise wavelength as closely as you can. Now, this is still a pretty old instrument, so it's not going to be perfect down to picometer, but it's going to be pretty stable for what we're looking for. And there is also an optical isolator. These kind of isolators are really important in DFB lasers and essentially in all kind of lasers, because if you don't have a good isolation there, you can just push the lasing out of the region you want, and it's going to create all kind of weird resonances and problems in there. So this optical design should be interesting when we take it apart and take a closer look at it. So that covers the DC biasing and stabilizing of the laser. But what about modulation? Now remember that this is not a coherent system. We can only modulate the amplitude, the intensity of the light in this device, and not the phase of the light. In order to modulate the phase, we need a much more sophisticated electro-optic device. We need something like a Mach center modulator, a significantly better type of laser diode with a line width that is actually compatible for that type of communication. Coherent optical communication is a whole other story. This is as simple as it's going to get. In fact, what they've done is that they are modulating the current through the laser diode directly. That's as simple as it gets. It's going to have some disadvantages, but for the bandwidth we're looking here, it's going to work just fine. If you modulate the current through the laser, you change the intensity of the light coming out, and therefore you can modulate the optical intensity. So in this case, they have actually some capacitors, even if there's a line going through it. That's just the error in the drawing. That's going to isolate the signal at DC, because there's going to be some DC voltage in here. You can apply an RF input over here. It's going to go through the capacitors, and there is some attenuator in here. I think this attenuator is just basically creating a good matching and a reasonably flat frequency response that can be well behaved, driving the laser diode directly. On this side, you can see there's an inductor over here. So this inductor and these capacitors with the attenuator make a bias T with a built-in attenuation with a good 50 ohm interface. And that's going to modulate the current in the laser diode, and the light is going to get modulated and it's going to come out on the other side. So you put an RF signal in, you get optical modulation. Pretty straightforward. There's a few other things in here that are also interesting. There's a temperature LED, which basically means that if the temperature drifts away, so if the whole thing is not stabilized anymore, it's going to tell you, so you know the wavelength has drifted away potentially, or there's a problem in the circuit. Now, as with all optical communication, the frequency of the light coming out here is 220 something terahertz. So it's really, really high. And you're modulating it at a few gigahertz. So the fractional bandwidth of the signal in that relationship is tiny. That's why fiber optic is so nice, because the bandwidth is enormous compared to the electrical bandwidth that you want to put in. But anyway, that's general for any optical communication. Then you have some power supply coming in. There's also a remote shutdown, and that's necessary for essentially all optical devices that produce laser power, because you may want to turn it on and off when you're not near the output. Even though this is a single mode fiber, you really have to poke it into your eye to cause any harm. But you should always be very careful, no matter what, with anything that generates laser, especially an invisible radiation like this. So that's the whole transmitter. So now taking a look at the receiver, then the receiver should do the exact opposite thing. Light is going to come into it with amplitude or intensity modulation, and we want to get the electrical signal back out from that. So in this case, fiber goes over here, some loop, and then there's a green lens. Now, unlike the name, a green lens is not a smiling lens, but rather a gradient index lens. How this works is that inside of the lens material, the refractive index is gradually changing. That means that the light is going to bend as it travels through the lens material. And by the time it comes out, it's going to be focused into where we want it to be. And in fact, the end of that lens can now be completely flat. It doesn't need to have a curved end. It is very good in sealing and compact designs. It also allows you to have some manufacturing advantages because of the flat end. So then that's going to get focused onto the pin diode. Now, I've talked about pin diodes in a different video. They're semiconductor structures. Sufficient to say that the pin diode is going to convert those photons into electrons. That's what we want. The electrons are the actual current. Now, pin diode also needs to be biased. In this case, they're using a pin diode with a relatively good dark current, and they're going to bias it with some reverse bias voltage on it. Now remember that this light is continuous with some amplitude modulation on top of it, which means that this pin diode, as soon as it's illuminated, is going to create some DC current. So this bias circuit is going to monitor that and stabilize that current and stabilize that voltage to where it should be, so the voltage across the diode remains where it needs to be. And then there is a amplifier in here. This is not really shown. There's probably multiple stages, but this amplifier is directly connected to this diode, which is interesting because that's going to see some of that current. But they've probably taken it into account because of the spacing, and they want to make sure it has a good frequency response. But then there is an AC blocking capacitor in here, and that's going to prevent any of the DC signal to show up at the output. So just like the transmitter, the RF output is also AC coupled only. Then there is some over illumination circuit detection over here, which kind of makes sense, because if you put too much light into the pin diode, it's going to become nonlinear, and if you put even more, you're going to destroy the pin diode. But this is just going to monitor the current inside of the pin diode and tell you, hey, you're putting too much, and it's going to illuminate this over illumination LED. Then there's some DC in and DC out, and that's just for cascading things, I think. And then there is the average power detector. This average power detector is basically also a function of the DC current going through the pin diode when it is illuminated. And that's about it. You get the RF signal back out. So in reality, technically speaking, the RF out and RF in, end to end, if there's a fiber connected, should look like a transparent system, because you're putting electrical signal in, you're going to get electrical signal out. And that's exactly what I'm excited to measure. Let's see if the whole thing actually works. And through the magic of spending more money, I actually went ahead and bought multiple of these, some of them which were broken, for the sole purpose of taking them apart. So we have an extra transmitter in here. I've taken the inside of it, which comes out as a single unit, out of this one, and this is the receiver. I've taken it out of that one, so we can completely disassemble these down into the optics and really see what's going on without damaging the working units that we want for our complete characterization. And this is also the perfect time if you want to support the channel through Patreon or PayPal. The link is in the description. It's pretty straightforward, and your help is appreciated, because my goodness, have things become really expensive. So here is the transmitter module. Now, based on the fact that we know the block diagram and how it works, we should be able to identify everything fairly easily. Here's the RF input coming in over the back, and you can see that coaxial cable going over here into our optical module. This also has a whole bunch of the cables, and you can see the end of the optical module there and the bottom of it there, which we're going to completely take apart and take a closer look at. All these wires are going to be connected to the backphase diode, the thermoelectric cooler, the temperature sensor, and everything else, all the analog interfaces. And the RF directly goes from a different path in there, which makes sense. We should be able to see inside how that's connected. And over here, this board at the top is going to be the analog control circuitry. Everything that does all the functions and loopbacks and everything else in there. There's a potentiometer here which adjusts the optical output power. This is the key that turns the laser on and off. That also is connected to this, which can disable the laser. And over here is the optical connector at the output. Now on the other side of this, there's another board, and this board looks like it's a DC-DC converter. So they actually do a whole bunch of voltage conversion over here with some switching, which is interesting. I'm not sure why they have to do that, but that's also going to create all the other voltage that they're looking for. Well, let's take this apart further. And here are the three sections that make up the whole thing. Interesting that they needed to switch in regulator. Perhaps they needed to go higher or lower in voltage with a particular efficiency. Nonetheless, this section is isolated from this section by being on a completely separate board. All the analog sensitive control circuits are here. Although it does seem like some control voltages for the temperature section is here too. This doesn't need to be super low noise. In fact, this probably draws a lot of current. So they want to put that separately from the sensitive analog setup. Here's the main module. That's all the optical magic. And there is a bit of a pigtail fiber in here, and I think there's a splice point. Yeah, there it is. There's a splice point. So there's a pigtail in here, and they've spliced it into the end of this fiber connector. And that's how they go out of this device. Pretty cool. There's nothing really interesting to see on these, but I do want to take this apart so we can see exactly what's inside. Also notice the entire custom-made machine aluminum piece in here from a single block. This must have cost a fortune just in machining alone, but I guess they could get away with it considering the price of these things back then and just the way manufacturing was done. But it's a beautiful piece of engineering. And here are the two modules where all the magic happens. The module on the left is the laser and everything that goes along with it. I've actually removed the cap from the top, and the one on the right side, you can just unscrew the cap. It's not destructive to take it apart. And we can go through all the different blocks. So this is responsible for the DC block, the attenuator, as well as the tuning of the RF pad to better match the input of the modulator here on the right side. So they've done this in quite an interesting way. These two vertical components are the DC blocks. They're just capacitors that they're putting on the edge to minimize their footprint. And then there's a strip line that runs down the middle, and the attenuator is thin film printed directly on top of that. This is really similar to a lot of the attenuators we've seen in the past. Nothing special there. But then they do have these little metal strips that are galvanically connected to the strip line in the middle, and they're bent upwards at different angles. And I think what they're doing is that by bending it, you're changing its effective capacitance. So you're essentially tuning that strip line. So the location of these, as well as the angle that they have adjusted manually, they all actually have different angles. I'm not sure how clear it is on camera, but they're all different. So somebody's been manually adjusting this in order to get the response exactly the way that they want. So they have to do an impedance transformation from here to here to have a flat frequency response driving the DFB laser at the end of the day. And I suspect that's what that attenuator really is there for, is to adjust and really help detune everything and make a quality factor lower so you can get a broadband response at a cost of some loss, of course. Now on the left side, you can see someone had a lot of fun trying to tune this network. There seems to even be some ferrite in there to absorb perhaps some radiation and create a good response on the inside. And then if you look carefully, there is one of these strips going along this side over here as well. So they've done a lot of tuning trying to get this response as good as they can. Down this middle over here, there's a vertical section. And the reason for that is because on the wall on the left side is where the detector, the photodetector is mounted. Remember the DFB laser shines in two directions. One direction is this way and one direction is that way. The DFB laser itself is very small. We're going to look at it under the microscope. And it's coupled to the fiber going on the left side. On the right side, it shines on the surface on that photodetector there, and that's how the closed loop is. And if you look also very carefully, you'll see that this little section is actually an island. That's because this is sitting on top of the thermoelectric cooler, and the two wires going through it are seen at the bottom over there. So this is where the temperature control actually happens. The photodetector is not part of that loop. There looks to be a tiny diode right there, which I think is what they're using for measuring the temperature. So yeah, pretty interesting. So we should really put this under the microscope to take a look. I really like this structure, but this is obviously really manual. I'm surprised that the angle of those things don't change over time and don't get detuned. We can measure the S parameter of this block by itself because it's just has coaxial connectors. So that should be interesting too. I want to see what response this has and how much attenuation there is. And here's a look a little bit on the left side of that wall. If you look carefully, right down there is a photodetector, and that's how they're closing the power control of the laser itself, making sure that it's producing the sufficient amount of optical power. Yeah, pretty neat. And here we're under the microscope, and we should see things much more clear now. So here's our fiber coming in, and there's some glue in here, which we will see under a different microscopy technique. And here is our DFB laser. And if you look at it, there's a line down the middle. So it's emitting in both directions on the left and on the right. And here's the island That's the division of the island. So this entire section here in the middle, that's what's on the thermoelectric cooler. And on the left side, if you look carefully, that's actually our photodetector. I can focus a little bit higher up on it so you can see it a little bit better. There it is. You can see it even has a wire bond coming off of it. So the light coming off of this shines on the surface of this, and it collects as much light as it can to estimate the optical power of the DFB laser. And then everything else is pretty self-explanatory. If you go a little bit this way to the right, we can see the fiber coming in. So that's the exit of the entire structure. And if you go left, we see that huge mess of a matching network and all the other stuff they've done there to really get this thing to be tuned. It's really quite interesting that they have to go through all this trouble. And here we are, going back to this section. What we can do is we can change the way this microscopy technique actually works, and we should see a different kind of image, which would be helpful. And here we go. So using dark field, we can actually see much better what's going on. So here again is our DFB laser. So you can see silver epoxy here is used to hold down the fiber. The fiber is transparent. You can barely see it over here. The island is much more clear. And on the left side, the detector. Now, if I go a little bit this way, you can see what they've done with the matching network a little bit better. Yeah, there's it's quite a bit of a mess in here. I think in my capture, it might be dropping a few frames here and there because I'm trying to record at 4K. So you can see everything much more clearly. So if you look at this a bit better, there's a lot of wire bonds here. So the high-speed path is coming right underneath this. That's interesting. So look, this is the bias point, but as well as the modulation. So the modulation is applied right where the bias is applied. That's to be expected. We saw that even in the block diagram. And the grounding structure around it, which surrounds the actual DFP, is also visible, connected across. Yeah, a lot of manual work in here and a lot of tuning. I wonder what they've done, why there are scratches here. This is clearly a ceramic of some kind package. Or if I go this way, we should be able to see. There it is. Here's our temperature sensor detector. And at the top, we should have a chip capacitor. Yeah, there you go. Some decoupling capacitor here, which we can focus on the top of it. There it is, wire bonded down. Nothing unusual. And if you go this way a bit more, we can see this little wall that they have. And that's the detector there. Now I can zoom in one more time so we can see the exact interface of the fiber coming close to the DFP laser, but it's basically just coming really close, and they must have aligned that and then just treated it so that it must be some active alignment, because by the look of it, I don't think this is automatic, at least not back then. Yeah, pretty cool. And here's a closer look at how the fiber comes close to the DFB laser. You can see the tip of the fiber is melted into a point and essentially emulates kind of like a little bit of a lens. It doesn't have to be so perfect, but it is very, very close in here. And on the other side, the DFB shines all the way, and then it gets caught by the surface of this detector. This is actually a very wide window. It's a pretty big point. That's why they can get away with not having any more lenses. And it just needs to capture enough light to estimate the power coming out. But obviously, these distances are very different. And I think we are focused fairly well at that interface, because the edge of the DFB laser and the tip of this fiber over here should be pretty well aligned. Yeah, it's a really crude method, but yeah, it works. And clearly, it does couple power. And here's a look at that DC block attenuator section. And now you can have a closer look at those thin foil pieces that I was talking about that are connected directly to the strip line. And you can see that they're all in different angles. That's why they're not all in focus. So they must have adjusted those. And they have certain spacing and so on that they must have experimentally known where to put. These black lines that you see are the actual deposited resistors. That's what makes up the attenuator. It's a pi network, as is obvious from the shape that it has. And even the connection to the coaxial port, which is over here, is using this film instead of wire bonding. Pretty neat. This must be some assembly technique they have. And if I keep going to the right side, you can see that there is a vertical capacitor. That's why that is not in focus. And then on the other side, you have another one of these foil pieces for tuning, and then the transition into the coax. So on the right side of this is just an SMA connector. And the transition is also pretty interesting into the substrate material here. Yeah, so a lot of trouble they've gone through to really put this thing together and actually be able to get the tuning. So I'm very eager to measure its S parameters. And moving on to the receiver, we also have a similar situation, except we no longer have that DC-DC converter board. We just basically have just the analog board. And all the magic is, again, in this box. Now, this model specifically may not have an amplifier, because there's a certain version of this where the connection to the coaxial RF output is directly on the photodetector itself. So once we open this, we'll find out if that's the case or not. The module that I have that we're going to do an actual testing on, that one does have the amplifier. So here's the fiber connection over here, and then it reaches all the way there. So I suspect there's a spool of fiber in here. Let's take this apart too. Yep, definitely. This entire machine section is just to hold this fiber spool there. And you may ask, well, why do they do this? Is because these connectors must have been already done with a certain length in mind for various things, and they're just reusing that. Splicing fiber is expensive, it takes time. So if you have standard length, you can just reuse those and you don't have to do them all over again. So now we can completely take this apart. I think the chassis is very similar in design. There shouldn't be anything unusual, but all the cool stuff's in there. And here's the optical receiver module, and it is another beautiful device here. And in the middle of it, at the bottom I should say, that's the green lens. So the fiber goes into that. And the alignment in this in X and Y must have been done actively again while this is powered and light coming in, and then they glue it in place. This is actually quite high up. I'll show you from the side as well. And the photodetector, the pin diode, is directly underneath in the center of this. So this indeed does have amplifiers. So you can see multiple stages of amplifiers here that are following that, and they're all AC coupled from each other. The first stage is DC coupled, followed by AC coupling, exactly like the data sheet said it would have. Now, in order for me to put this under the microscope and take a closer look at it and see the pin diode also, I have to actually break this off because it won't fit under the microscope. There's a lot of height in it. There you go. You can see very well exactly how that structure is. Look at that. That is pretty cool. There's also this thing sticking out, which is part of the machine housing, so that's going to be pretty difficult to put under the microscope. But look how beautiful this thing is, the amount of work that's gone into this. Now, nowadays, you don't have to go through all this trouble. There's a lot better assembly techniques now that you can use for optics. At this cost point, you wouldn't be able to sell anything. So things have certainly changed a lot in the past. What is this, 1991? Yeah, so quite a long time ago since then. Yeah, pretty neat. Let's see if we can put this under the microscope now. So here you go, I broke off the green lens, and look at that. You see how the end of it is completely flat? That's the real beauty of this type of gradient index lenses. And you can see some coloring that happens because of the index of refraction changing. So yeah, that is the magic. That's our lens. It's kind of unusual to see a lens with a flat end, but that's what happens when you play with the actual doping of the material along the propagation path of the photons. Pretty cool. And now looking at the receiver, right in the middle of the page is the aperture of the pin diode. Right over here, that's where the light is focused using the green lens. And it's sitting on a pedestal higher than everything else. That's why it is in focus and everything else is not in focus. And if you look, the connection coming out of it is this mesh ribbon, which we've seen many times from HP and Azure and some proprietary thing they're using. I actually have never seen it in anything else, but they really like to use that. It must be a good compromise between creating a transition and having the capacitances and inductances well behaved. Now, just like the data sheet actually said, the biasing network, let me focus on that, is right here. So there's a big capacitor in here that provides the AC ground for the photodetector. There's some resistor in here for biasing. And interestingly enough, the first stage amplifier, which looks like a single device, is in fact DC coupled directly through this interface. So this device does see the DC current coming out of the photodetector under constant illumination. It has to absorb and process that. That signal is probably well managed over here. So all the biasing circuit magic is around this point. And if we go north, I'm actually looking at this for the first time here. I hope I didn't damage it too much, but yeah, you can see that ring there that I removed, glue there that is used for aligning is clearly visible. So we have a AC block, so every other stage now after this is not connected at DC anymore. Everything is separate. There we go. There is another pair of devices, so we've got one amplification after that again, another DC block, another stage of amplification, and one more time, and then one more pair of stages here, and then finally I think we go out. There it is. Yeah, that's where the coaxial connector is. And coming down, these are all the same stages. They're just repeating it. And you can see all manual wire bond and then everything. Oh, look at that. There's a cool structure here. Looks like they've made a little makeshift inductor using wire bonds, and that looks like to be on the input side. Yeah, so they have some inductive peaking here to boost the frequency response at some point. So there's a little resistor in here in series with this inductor. Very classic inductive peaking techniques. And then going over here, are they repeating that structure everywhere? Let's see. So they have it here for sure. Do they do this in every stage? Yeah, there it is. Here's one more. This doesn't look like it has exactly the same amount of inductance, so they're probably tuning every stage a little bit. Might be some staggered tuning going on here, but it's not very obvious to know just by looking at it, but it might be because the actual diameter of the loop isn't so obvious looking at it from this angle. Yeah, look at that. So much work to get something like this working, but you can appreciate, hopefully, exactly how it is put together now. So let's get to the fun characterization stuff. Now the first thing to do is to measure to see if this thing is even producing an optical signal, and if it is in the right wavelength, which should be around 1310 nanometer. Now if we don't do this, we will never know which part of the system isn't working, so we at least have to verify the output of this one. But in this case, Siglent doesn't make an optical spectrum analyzer, so we have to use something else. And to verify the optical performance, we're going to use the Yokogawa spectrum analyzer. This is an optical spectrum analyzer from 600 to 1700 nanometer. Should be pretty easy to see if the right wavelength is coming out. And this instrument is not using an angle connector, which is nice. So first thing first, we clean the fiber very carefully, always first step, and then align it, and then we should be able to easily measure the actual wavelength coming out. Let's see if we can find our signal. I'm going to turn the laser on. And here it is, and the light is on. Let's try the auto function. Normally, I don't like to use auto in spectrum analyzer, but for optical ones, it tends to work well, especially because it needs to zero in the signal. There it is, look at that. I think it found something. Yeah, let's do a peak search. And the wavelength is 1320.942 nanometer. So it's supposed to be 1310. So that's a big difference between the two wavelengths. Now it hasn't warmed up quite a bit, and I think it might have drifted over time. We could do some adjustments in the thermoelectric cooler and try to bring it closer to where it should be. But really, for the sensitivity between 1310 and 1320, it's going to make no difference. This is the direct detection system. Our receiver is sensitive across a much, much wider wavelength. And we can see that it has a reasonably okay here line width. And what is it? We're looking at a span of a pretty small span. Yeah, so you're only at 1 nanometer. So what I can do is I can actually stop this and enhance and increase the span a little bit. Let's go, let's say, to 50 nanometer. And let's see what that looks like in that situation. Let's do a single measurement. Let's see what kind of spurious modes we have. Look at that. Those are all the different little tiny modes. Likely they're not lasing very much. There it is. And that's our main peak and a whole bunch of other ones. So there's a massive difference here. So this is a reasonably good DFB laser. It's achieving what it's supposed to. The peak amplitude here is what? We're getting around 2.5 dBm of output power, which is normal for this kind of system. And, the spurious modes are also pretty good. So it should work perfectly fine for what we want. So now that we have verified that this thing does produce the correct laser wavelength and power, what do we do next? Well, if you have a lot of optical equipment, you can actually individually characterize these separately, meaning characterize this thing's electro-optic response and this thing's optoelectric response. But that requires a lot of advanced optical equipment. What if we aggregate them and just combine them together? Well, the disadvantage is that if you measure the response of this from end to end purely in the electrical domain, you won't know what the individual responses are, just a combined response. But that means that you can stay completely in the electrical domain. And for that purpose, we can actually measure the S parameter of this when we have a fiber connected from the output of this to the input of this. So we get the electro-optic and optoelectric response simultaneously. And for that, I'm going to use the Siglent Vector Network Analyzer. This is the SNA 6000 series, 4-port, 13.5 gigahertz with port extensions. These are fantastic instruments. I've been using it more and more. I have to say, I am pretty impressed with what Siglent has done in the RF domain. They have a lot of equipment, and we will see more of that in the characterization. They're also compatible with ECAL modules. So I've already calibrated this thing for port 1 and 2. Port 1 goes to the input of this guy, and port 2 is connected to the output of this one. So we should be able to measure the aggregate S parameter. Let's see what it looks like. And here we have the S parameters with the laser turned off, and you can see that the S11 and the S22 look pretty good. That's because the S11 is the electrical input of the transmitter, and S22 is the electrical output of the receiver, which have no bearing on the presence of the laser in this case. And the S12 and S21, they're way, way too low, so we don't see anything at the moment. So let's go ahead and turn on the laser and see if we get a response from this. And here's the laser. And let's see what we get. And check it out. We get a nice response on S21. Now, there should be nothing in S12, and it is, you can see, it's well below minus 50. And that makes sense. You can auto-scale this. Yeah, it's sitting at minus 100 because this is a fiber optic link. So there's nothing coming back the other way. And that makes perfect sense. There's essentially infinite isolation here. And if I go over here and enable a marker on this, we can see what kind of bandwidth we actually have. Let me turn on a marker here. There you go. So this is supposed to be only a 6 gigahertz system. So here's the round DC. So we have a gain of about minus 8 dB, and 6 gigahertz is somewhere around here. So this has a lot more bandwidth than 6 gigahertz. Now it does get a lot more ripply, and it does have some peaking and some variation in there, which is going to be pretty bad in terms of group delay. But yeah, it's pretty flat from DC to around 6 gigahertz. So even though this is a completely back-to-back system, remember that this includes all the front-end electrical on the transmitter, the actual modulator and the DFB laser, and of course the fiber that's going through, and on the other side, all the receivers and amplifiers and everything in there is actually included in this response. So it's not so bad. Now we do have about minus 9 dB here or so, and that's just a response back to back. But this does actually make sense or not. Is this in a linear region? We can actually check this out. So let's do some basic verification to see if this system is operating in an appropriately linear fashion. And one way to do this is to introduce attenuation in the optical domain, which is exactly what I've done here. The output of the laser enters this optical attenuator, which I can set to any value that I want. And you can see I have set the reference wavelength to be 1320 nanometer. And the output of that then goes into our receiver. Notice how the connectors on the optical attenuator are angled. They're APC connectors, but the connectors on these are straight pieces. So the fibers have to convert the two ends when they're connected. And all that should work perfectly fine. I can adjust the attenuation in here, which changes the amount of optical power arriving at the receiver. And then we can measure the appropriate S parameters and see if that relationship is actually correct and it conforms to the theory. If it does, we know that the system is appropriately behaving like it should be. So here's right now the S parameters with the optical attenuation set to 0 dB. But if you notice, we do have a lot less gain than we had before. And that's because this optical attenuator and the new fiber connections have some inherent insertion loss. So there is some optical power that is lost in the optical attenuator even when it's set to 0 dB. So we do get some lower amplitude. But that doesn't matter because we want to do a relative measurement and see what happens if we apply a known amount of optical attenuation and what happens to the S parameter. So right now at around 500 megahertz or so, our gain is minus 16 dB. I'm going to introduce 3 dB of optical attenuation, which means half the optical power. Let's see what happens. Here is 3 dB. And look at that, it went to minus 22. So we lost 6 dB of gain in our S21 for 3 dB of optical attenuation. I can remove the optical attenuation again. There you go, back to 0. And look, it went back to minus 16. But does that make sense? Well, it does, because if you look at the responsivity of a diode, a pin diode's responsivity is measured as amps per watt. So what we've done is that we have made the watt half, which means we've made the current half. So if you make half the watts and half the current, well, you lose actually 6 dB of gain for half the optical power. This also indicates the importance of preserving optical power and how important optical interconnect actually is, because the loss of a dB for optical power is actually pretty bad for your system gain. But this is consistent, which means the entire system is running linearly and is conforming to the theory. Before we move on to other measurements with the optical devices, let's quickly measure this attenuated DC block as well and see what kind of an impedance transformation and frequency response it has. Remember that this sits right before the DFB laser, and that's where the RF signal is actually applied to. So the response is interesting. Of course, S21 and S12 are going to be the same for a passive device like this without any directivity. And then we see that there is some impedance transformation. Now remember that we don't know what the impedance of the DFB laser is, but nonetheless, we can see that the impedance looking on each side of the port of this device are not the same. At low frequencies, it looks like the attenuation is only about 2 dB or so in a 50 ohm environment. And then as we go further, there's some weird, unusual transitions, and that's probably where the tuning comes in. They must have individually tuned those taps, looking into the entire structure to make this frequency response as flat as possible. If you look at the impedance facing the outside, we do have almost 50 ohm, but then on the other side, we have, you can see quite a bit of an inductive behavior at this frequency, and at some point it becomes capacitive. It's kind of rotating around the center there. And this really only rated up until about here. The rest of this is nonsense. You can see there's a big dip in here, which is going to eat into the frequency response. But yeah, so they've clearly adjusted this to make it work with the DFB laser. A lot of manual work, but then ultimately what the user cares about is a flat frequency response. And even for us, the back-to-back TX, RX have a reasonably good flat response. So they've done a good job. So next, let's characterize this electro-optic link using more complex waveforms. In particular, let's measure its linearity and see what kind of signals we can process through this electro-optic link. Now, to excite the transmitter, we can use something like a vector signal generator. This particular one is the Siglent SSG 5000 series, which goes up to 6 gigahertz and has a built-in dual arbitrary waveform generator. I've done a full teardown and review of this instrument. It's great to be able to create multi-tone and various modulations directly from the instrument, which we will do. At the top over here, I also have an arbitrary waveform generator from Siglent. This is the SDG 7000 series, 5 gigasample per second, 1 gigahertz of bandwidth. We should be able to create much higher bandwidth modulation as well as NRZ signals directly from this, which we will use next. Now, on the analysis side, we're going to use, of course, a spectrum analyzer. In this case, the Siglent SSA 5000 series has a lot of different software functions and personalities, including real-time spectrum analyzer. We can do a lot of our analysis directly on this instrument and even do the modulation, which we will see. So first, let's measure the linearity of this entire setup. Now we can do our characterization somewhere in the middle of the band. So here I've chosen 3 GHz to be our carrier frequency. Now in order to measure linearity, we need to generate 2 tones, which we can very easily do with a built-in arbitrary waveform generator. If we go over here, we go under modulation and multi-tone. You can see I'm generating 2 tones that are 7.5 MHz support, and I'm placing them on one side of the sideband. So we should be able to have 2 tones centered around 3 GHz. Now, first thing we need to measure is to measure the linearity of this instrument by itself, because we need to know what are its intermodulation terms, so we can compare that with the intermodulation terms after it goes through the electro-optic link. So first we're going to connect this guy directly to the input of the spectrum analyzer, bypassing the optical link completely, characterize that, and then we're going to do it through the optical link. Should be interesting. And as expected, with the vector signal generator directly connected to the spectrum analyzer input, we can see the 2 tones we're generating around a 3 GHz carrier. We also see the intermodulation term on the right side and on the left side. Now these are not symmetric. This is a very, very subtle limitation, and that's because with the current firmware of the vector signal generator, I cannot place these 2 tones further out, which means that the IM3 terms and the LO rejection on the left side land on top of each other, and that's why this is larger. This is a very, very subtle problem that hopefully they can adjust later so that it gives more flexibility to the kind of 2-tone signal you can generate using this instrument. But nonetheless, it works reasonably well the way it is. We really can't just focus on the upper one, assuming everything is symmetric and it should be fine. So in this situation, we can measure a TOI or intercept point and the intermodulation directly with the built-in software. If you click over here, you see all the software personalities, which there are a lot of. This instrument has a lot of options. Everything is enabled here, but you can do pretty much any measurement you want. And you can actually add them in a list of windows and jump between them once you configure them, which is really, really helpful. So I've already configured the TOI here. We can switch to that, and it will bring us directly to the TOI window. Here it is, and it's going to do this measurement for us in the background. We can in fact just restart it because it's doing some averaging. And again, here you can see the asymmetry. And in fact, you can see the asymmetry here in the lower third and the upper third measurement as well. This is minus 48, 49 dBc. This is minus 60. So this source on its own, when it's generating a 0 dBm aggregate power, is pretty linear. Minus 60 dBc is very good. TOI is 26 dBm. So we should remember this number and see what the optical link does to this, because it can never get better than this. It's always going to get worse if there are limitations from the linearity. One other thing we should do is we should increase the power from our source to see how it behaves when we're putting out a lot more power, to see if this number gets any worse. So I'm going to increase that, go from a 0 dBm to, let's say, 12. And here is 12. And we can restart this measurement, and let's see if anything has changed. Here's the restart. Okay, so we get a little bit worse. IM3 minus 57 is still very good. TOI is huge, 36, 37 dBm or so. So that's going to be our reference. So now let's go and swap things out and put this signal directly through our electro-optic and see what happens. And here is the result. Check it out. This signal is now going through our electro-optic and optoelectric conversion. This is with the synthesizer set to 0 dBm. A few important things to note. First of all, the total power coming out is now lower. That's because we know from the S parameters that this link has about 8 or 9 dB of loss, which matches this perfectly. But check it out. The nonlinearity is only marginally worse, which means that this electro-optic link is very, very linear. It's almost as linear as the source that we are actually using, which is nice, which means that it can process all kind of interesting analog signals. And that's exactly where radio over fiber comes from, because you should be able to put complex modulation directly through the fiber like a radio signal would. You can center that at anywhere in the frequency band that this thing has bandwidth in, which is exactly what we're going to try next. But let's increase the power to 12 dBm and see if there is any limitation with higher signal coming in. So I'm going to go to 12 dBm, and let's see what happens. In this case, we have to again restart this. And let's see. Okay, look at this. So now we do see a bit more limitation, and look at that. The two signals are now the same. The reason they're the same is because the IM3 is now dominant. So this is getting a little bit more nonlinear, but it's still pretty good. We should be able to send some really high order modulations through this signal at this power, which would be pretty amazing. And you can see it's putting out over 0 dBm total power now. So this is a pretty good link. Now that we know this, let's go and configure a complex modulation and see if we can do the quote-unquote radio over fiber using this system. Now, configuring the SSG to generate for us a complex modulation is also pretty simple because it is built into the instrument directly. We can go under custom modulation over here, and we can select the modulation that we want. So in this case, I've chosen 256 QAM, which I think is one of the highest. You can go all the way to 512. So 256 QAM modulation, that's 8 bits per symbol. We can also go back and set the actual data source. So I'm choosing 32 megasymbols per second. So this is a 256 megabit per second link we're trying to set up with a fairly complex polynomial here as the source. Everything else is already set up. So we can go ahead and turn this modulation on. So now we're no longer sending two tones, we're sending a QAM modulation. And we want to demodulate that and take a look at and see how good the constellation looks. And now looking at our spectrum, we do see that we have a broadband modulation corresponding to our 32 megasymbol per second 256 QAM signal centered at 3 gigahertz. Now we can use the markers in the unit to measure how much power is coming out of the receiver. And in this case, I've done that, and you can see that it is minus 1 dBm or so. So this modulated signal should be able to be recognized by the software of the spectrum analyzer and be demodulated live. And I've already set that up as well, because that's one of the personalities of this instrument called DMA. And we can go and look and see if it can successfully demodulate our signal for us. And check it out, there it is. Here's a 256 QAM signal. The constellation looks pretty good. Here's the spectrum again, as well as the eye diagram on the iPad. And we do see that EVM is around 10% or so. Now, one thing this instrument doesn't have, and I couldn't find, is equalization. Now, it's really important for some live adaptive equalization to actually be part of this personality for it to be truly useful, because it's impossible to get a good EVM, especially at these high order constellations, without at least some kind of correction. So I hope that they add that. But you can see how easy it is to configure this and take a look at a constellation. Now I can also mess this thing up, for example, by lowering the power. If I lower the power from the transmitter, eventually we will run into the limitations of SNR. So here you go. If I go to, let's say, at some point, there it is. You can see that our SNR is now much worse. We're going to have a hard time capturing that. Now we can optimize the spectrum analyzer to try and do it, but it is indeed measuring this live. So this is, in fact, what radio over fiber is. You can imagine a situation where, for example, you can take a Wi-Fi signal, put it into the transmitter, pass it with a fiber over a long distance, put it back into the receiver, and then put it into an antenna. So you can transport RF signals over very, very long distances through the fiber channel as if it was through the air, but it's going to be a really well-behaved channel. So these DFB lasers are really linear and perfect for these kind of applications. Of course, radio over fiber is not new. It's been proposed for many, many years, but this is a live demonstration of that. So next, let's do a simple digital link through our optical interface. Now, after all, these kind of direct detection links generally are used with a simple NRZ modulation. And we're going to use the Siglent 7000 series arbitrary waveform generator. Now, this is a fairly sophisticated instrument because it can do essentially any kind of waveforms between its IQ outputs. So in this case, I'm just simply choosing a PRBS, which is an NRZ type of signal, so it's going to be pretty straightforward. This is a 5 gigasample per second unit. For a good rise and fall time NRZ signal, we can go all the way up to 625 megabits per second. We can control the modulation depth, the amplitude coming in, and of course the termination. This also has completely differential outputs, which I really like. And I like the way it is handled inside the unit, because when you're using it in single-ended output, it automatically disables the other one and terminates it appropriately, so you don't have to connect it to anything. So switching between differential and single-ended is handled really well on this. There are tons of different features inside of this, which we will see more and more as various experiments come in the future. For now, we're going to see what kind of NRZ signals we can get from this through our optical link. And here is our new setup. We're going to take a single-ended output, directly put it into our optical modulator, and then on the receiver, we're going to go to the Keysight MXR. Now, the reason I'm not using a Siglent oscilloscope for this is because I actually don't have any Siglent oscilloscopes in my lab. But if you look at their portfolio, they have a wide range of oscilloscopes that you can choose from, especially at this data rate. We should be able to do some sophisticated eye diagrams using their instruments as well. But in this case, we're going to use the Keysight MXR 608A, which I've done a complete teardown and review of as well, to capture our eye diagram and plot it. At the same time, I have the detector output on the receiver going to the Siglent 6.5-digit multimeter. So when I enable the laser, we should be able to see the actual detection voltage reflect the fact that there is laser coming in. And then by turning the signal on and off, we might see a minor change in the detector power, because the average optical power might be slightly less when there is modulation. Let's take a look. So here's the detector voltage with no laser. I'm going to turn the laser on. And here's the laser on. And let's see. Want to stabilize? There you go, 4.8 volts. That's a lot of LO power coming in, LO in this case referring to the laser carrier. Now if I turn the modulation on, the average optical power will go down ever so slightly. Take a look. Here's a modulation on now. Look, we see a tiny change, which of course with the 6.5 digit multimeter we have absolutely no problem detecting. If I turn the modulation back off, there you go. You can see that minor change is happening. This is also telling us that we're doing a good job maintaining our total LO power through the link when the modulation is there. So the signal amplitude is good. Let's take a look at the actual eye diagram. Okay, so here we are with the display of the MXR. The laser right now is enabled, but the modulation from the Siglent arbitrary waveform generator is not. So let me turn on the NRZ modulation and see what happens to the signal. And there it is, check it out. That's a pretty nice looking eye diagram. Now we shouldn't be surprised that the eye diagram is as good as it is. It's really wide and perfectly open. Doesn't have a lot of noise, the jitter is under control, and the reason is because the source of the eye coming from the arbitrary waveform generator is very good, and it's not going to be affected much by this optical link because the bandwidth of the 625 megabit per second signal is pretty small compared to the overall bandwidth of this optical link we have. It's over 6 gigahertz, and the group delay variation within this bandwidth is also pretty small, so we're not getting a lot of ISI. So both in terms of noise and ISI, we're in good shape, and that's why the eye diagram looks really nice. So we did two things. We did radio over fiber at the carrier, we did a modulation around that, and now we're doing direct detection directly from an NRZ signal, which is a broadband baseband signal. So yeah, it works really nicely. But let's see if we can really push the limit of this and see how much data we can crank through this fiber given the bandwidth that it has. And for this experiment, we really have to bring out the big guns. We need to generate a modulation at a very high baud rate as well as a carrier frequency. And for that, we're going to use the Keysight M8195A. This is a 4-channel, 65 gigasample per second arbitrary waveform generator, and it has digital upconversion capability built in. Essentially, what this means is that I can generate an IF carrier and put a broadband modulation around it because it has over 35 gigahertz of bandwidth, so we can do pretty much anything we want with this. This is going to be controlled with a software called IQ Tools to generate the modulation we want at the carrier, which I will show you. These are all differential outputs. We're only taking one of the outputs, feeding it to our transmit laser. On the receiver, we're similarly taking that and feeding it into the Keysight MXR 608A. With the combination of these two, I should be able to now get a much wider modulation and a lot higher spectral efficiency to get more data through the fiber. So let's go to the computer and take a look at the result. So here is the soft control panel of the M8195A from Keysight. Now you can do a lot with the soft control panel already, but the nice thing is that there is a free software called IQ Tools, which Keysight provides, and you can even get the code for it in MATLAB that allows you to generate all kind of various modulations. It's really nice, including radar, OFDM. The fact that this is freely available is pretty amazing and gives a big advantage to the arbitrary waveform generators from Keysight. So here, if you look, we do have 64 gigasample per second, and we're generating a 4 gigabaud modulation. So it's reasonably broadband signal. A lot of points are in this modulation because we do have the memory to support it, and it's going to have a 64 QAM modulation format. So 4 gigabaud at 64 QAM, that's 24 gigabit per second equivalent. So it's a reasonable amount of data over a narrow channel. But here's the important part. We can generate a carrier directly from the ARP itself. So we don't need an external LO signal because this is going to be built into the sequence of the digital modulation. We can do this because we have such a high sample rate, and we can easily generate a carrier directly in there. In one go, the arbitrary waveform generator can do all of this. So I've already done that and downloaded it into it. We're using the channel 1, as you can see, with a full-scale output of 1 volt. And that's going to go into the laser. And in order to analyze the modulation capability, we're going to use the Keysight VSA, which is a vector signal analyzer with a custom IQ option. And you can see we are demodulating our 64 QAM signal without any issues. We're also applying equalization on top of that. You can see the SNR is around 25 dB or so, 5.5% EVM. And you can see also the spectrum centered around a carrier of 3 gigahertz. So all of that makes sense. The channel response as well as the equalization shape and the EVM as a function of time are also being displayed here. Now VSA is a pretty sophisticated software with a lot of capabilities which I have covered on the channel before. Now if you note, the EVM here around 25 dB or so is at the threshold of what this can do. But that's because this is a limitation of the optical link. The actual arbitrary waveform and the oscilloscope, their floor EVM is considerably better than this. And that's because we have some noise limitation, a little bit of nonlinearity limitations at the amplitude I'm inputting into the laser transmitter, but primarily we are equalization limited because the frequency response of this optical link wasn't very good, and it did have group delay variation. But nonetheless, you can see that putting 24 gigabit per second through that channel is really easily possible if you have the right equipment and you set it up correctly. And there you have it. I hope you enjoyed this extensive teardown analysis and characterizations of this optical link. Now, even though these modules themselves are obsolete, the metrology techniques as well as the concepts covered here, those are timeless and they are still relevant to the applications today. At the same time, I also wanted to show the capability of the Siglent instruments ecosystem to characterize something like this completely. And whenever something was missing, of course, we used another vendor. But it's pretty important to see how various instrument makers approach having a complete range of equipment to cover all kind of metrology needs, and hopefully that you found the Siglent ecosystem interesting, because I think they've done a lot of good work in this space, and competition is always good for the end consumer. Let me know what you think in the comment section, and as always, if you want to support the channel, it's pretty easy. The link is in the description, and your help is always appreciated and put back into the channel. I'll see you next time.